So let's close out this chapter by looking at a couple of more details. The fossil fuel industry continues to be a part of the methane emission. This is another way of looking at the methane sources in million tons of methane. This is from the International Energy Agency. There is biomass burning, other sources, waste, landfill, etc. Energy production in terms of gas, coal, oil, and bioenergy. Agriculture remains a significant source of methane, especially as rice paddies, for example, and waste handling, and wetlands. So energy industry, obviously, it's got the gas, coal, oil productions emitting methane, as we talked about, which is either just released into the atmosphere or fired off, and so on. And the question about hydrates remains. As we said, in the Paleocene, Eocene thermal maximum, the isotopic evidence wouldn't allow us to conclude that it was actually all from methane release from hydrate perturbations, even though that was proposed as one of the hypotheses for explaining the rapid warming that we saw. Not as rapid as what we are doing now, in fact, but the question of how long it would take for it to if something happened and there was a worldwide perturbation of the hydrates, that's what you would need to produce a substantial slug of methane in the atmosphere. There are very few scenarios in which this would happen, so the probability of this thing is low. But assuming somehow it happened, you would look at the slug of the spike in PCO2 and methane and the radiative forcing, and see how long it would take for it to equilibrate out in the carbon cycle overall. So with hydrate and without hydrate, the CO2 slug of this magnitude would have different equilibration times. Obviously, adding methane from hydrates would elevate the PCO2 throughout the life cycle over 100,000 year time scale. And there is just the methane spike, which would go off quickly because methane quickly gets radically oxidized and moved into CO2. So here it's the feedback, here it's just methane. So obviously methane is highly oxidizable and is going to get wiped out somewhat faster. Instead of going off here beyond 100,000 years, this would disappear in about 40,000 years for the spike here. And radiative forcing just from methane versus PCO2 with no hydrate and hydrate would have very different impacts. So methane from hydrates is a concern, but not really a very large probability of a worldwide perturbation of the buried hydrates, even though they have massive amount of carbon buried in them, right? They are unstable in some places like Siberia, where the depth of the hydrates is as low as 200 meters because the temperatures are very cold. In most other places in the map that we looked at, most of the coastal regions, in fact, the depth will be more like 500 to 700 meters. But 200 meters is rather too close for comfort in terms of coastal perturbations, right? So methane degradation, radical chemistry turns out to be a very important part of it. Just in terms of basics from this course from this university, Elmhurst University, we have the methane structure here, carbon and hydrogen. The electrons on the outer orbit, called the valence electrons, are readily available for having covalent and other bonds with other elements. So there is ammonia, which has an unpaired electron in the outer orbit, which is ready for reactions, but it's not charged. Water has the electron exchange between oxygen and hydrogen, and there are reasons why this has a certain angle of 105 degrees and so on, basically because of the repelling forces between the unpaired electron pairs in the outer orbit. So this makes the water molecule bipolar. So that's why it easily dissolved many things like salt, for example. And when you have non-polar molecules like oil, they don't dissolve because they cannot be split by the polarized water molecule, and there is hydrogen fluoride. And that's our friend carbon dioxide, which is symmetric but has a of course oxygen with its paired outer orbit electrons which have valence or available for reaction. But generally symmetric molecules like N2 and O2 are not greenhouse gases, but CO2 is, because it has a bending vibration mode which is sensitive to the photon in the infrared, which makes it a strong greenhouse gas. So the reactions that are critical are that the OH radical, which is not charged, so it has split from hydrogen, from water molecule. So you have taken away one H, so you have left the unpaired electron that is very hungry, so it'll react with methane to produce methyl or CH3 with an unpaired electron, no charge, plus water molecule. And methane also can react with oxygen, obviously get oxidized through carbon monoxide and then carbon dioxide and produce water molecules. Right, so you have multiple reactions, and each reactions can be split into steps, as well as we did before for carbohydrate oxidation, for example. Nitrous oxide molecules, which are produced from fossil fuel emissions from burning, from cars and vehicles and so on, are the source of this hydroxyl radical. If hydroxyl is a detergent which quickly reacts on fast timescales with methane and others to produce water molecule, then why doesn't it get exhausted? Basically because there are other sources of hydroxyl molecule in the atmosphere, like NOx, that are being produced from emissions, which in the presence of UV, which is the energy source, can produce hydroxyl radical and nitrous oxide radical, NO2 radical, which continue this production of OH, which continues to react. So here you have NO2 with the unpaired electron producing or unpaired electron reacting with UV light to produce NO and oxygen, and that oxygen is going to react with oxygen molecule to produce ozone. And this is the danger of having NOx in the troposphere, that in the presence of water they can do damage by producing ozone, which we said is bad for health, bad for crop yields, and of course it's a greenhouse gas. So radical chemistry in the atmosphere is very complicated, but the main thing to remember is that methane is constantly going through these radical chemistry and degraded, in addition to being directly converting into carbon monoxide and carbon dioxide. So OH radical is formed in the atmosphere when ultraviolet from the sun strikes ozone in the presence of water vapor. So we are talking about the troposphere, not the stratosphere. The initial reaction involves photolysis of ozone by solar radiation. So you're producing ozone from presence of NOx, which is a byproduct of fossil fuel burning, and then that ozone is reacting with UV light to produce produce oxygen and this oxygen molecule and oxygen atom, then oxygen atom is going to react with water vapor to produce two OH radicals, which is going to react with methane to produce its degradation. Okay, so those are the main reactions. This is the Lewis dot structure, which is important for understanding all these radical chemistries, which I'm not going through in detail, but read it in the book and many other sites which provide these details. As we talked about hydrogen and oxygen combining to form water molecules, there is hydrogen with one electron. Electrons have these spins and they are always trying to be paired up. H has one electron which is looking for an electron to pair up with. So oxygen donates one electron each to the two hydrogen molecules, and it has two paired electrons still in the outer orbit. And when you produce hydroxyl radical, you have one unpaired electron left here, and oxygen with hydrogen with one electron is not going to react, whereas hydroxyl radical with one unpaired electron is going to be very reactive, which is what makes it the detergent of the atmosphere, reacting with all sorts of things. So here is the nitrogen radical, for example. You have to basically figure out why the extra electron goes here when you split water molecule. Basically because that's what the oxygen has two bonds, and you have removed the hydrogen with its one electron, unpaired electron, and so the other unpaired electron has to remain with OH, which makes it very reactive. Okay, so it has an unsatisfied spin pairing here, which is similar here. So you have to do the homework to figure out why the this radical has an unpaired electron here. So these are all paired. There is one unpaired here. Okay, so radical chemistry is kind of interesting, but I'm not an expert on it, so I'm just kind of presenting it for you to read up more if you want to follow up on it. But it is an important part of the radical chemistry for methane, which is why methane doesn't last very long in the atmosphere. Okay.